Hey there, I'm John and you're watching the presentation video for my final artificial intelligence project, which was to develop an AI controller for Threes, a puzzle game for Android, iOS, and Xbox One. Threes uses a continually shuffled 12-card deck consisting of 3 4-card groups of 1s, 2s, and 3s, for a total of 4 1 cards, 4 2 cards, and 4 3 cards. Starting with one of these 12-card decks, all the cards are dealt randomly on the board and a new 12-card deck is created and shuffled, and the top card is flipped over for the player to see. The player then must choose a direction to swipe, which will shift all of the unobstructed cards on the board in that direction. A card is obstructed from moving in a particular direction, either by a wall or by another obstructed and unmergeable card. Except for 1s and 2s, which may only merge with one another, cards may merge with other cards of the same value by shifting on top of them. This merging process creates a new card with a value that is the sum of the 2 cards which went into it. After shifting the cards in a particular direction, the top card of the deck is placed randomly on the side of the board opposite the direction of the player's shift. If the deck becomes empty, it is refilled as needed with the same 12-card deck. This process is repeated until the player can make no more moves that change the board. In addition to the 12-card deck, a bonus card deck is filled up as the game progresses, starting once the player has reached the 48 card. Once the bonus deck has at least 1 card, there is an ongoing 1 in 21 chance that the next card to be flipped will be from the bonus deck. If this is the case, the player will know only that the next card is from the bonus deck, instead of knowing the actual value of the card. Unlike the normal deck, cards from the bonus deck are replaced as soon as they are removed, meaning all bonus cards are equally likely given that the next card is a known bonus card. Since all non-player initiated game events in Threes are stochastic, I use the Expectimax algorithm to build my AI controller. This algorithm takes as input any state of the game and returns the best move for the state. How it decides which move is best can be divided into 2 parts. First, it creates a game tree rooted at the given state. Like Minimax, this game tree is scored from Max's point of view, and Max always works to maximize his score. But unlike Minimax, there is no assumption of the worst-case scenario. Instead, a weighted average is used to compute the maximum expected utility of each move. From this root, successor states are generated and the tree is traversed state by state until a terminal state is found or the depth limit has been reached. The resulting boards at the end of the search limit are then scored and propagated back up through the branches of the tree to the root, calculating the maximum expected utility of each move for the original given game state. While the process of traversing the tree in and of itself provides much of the power for the algorithm, it is heavily dependent on how utility is defined in terms of a given game state. For my controller, I tried to model my own approach to playing the game, which is very much heuristically based. I rarely need to consider more than 2 moves ahead, and most of the time I use my prior knowledge of the game mechanics to choose my moves, rather than carefully selecting between chains of events that may or may not happen. Thus, my utility function extensively analyzes the game board using a few different methods of evaluation. Though the complexity of this function has limited my search depth, its analysis performs well without having to search too deep. This all comes together in my custom Threes AI web app, which is written in Java using Google Web Toolkit and is online for anyone to play with as of this video's upload. Thanks for watching.